Here we will be discussing a most important and fundamental topic which a fluid mechanics student must know. Is going to be discussed simply the Newton's law, that is, force is required for an acceleration or F equal to ma is applied in a three-dimensional coordinate system, and we will be getting basically Navier-Stokes equation, then Eulers equation, and from that we'll be concluding with Bernoulies equation. That is a must thing. Okay, and so what we will be starting with, apply Newton's law in a three-dimensional coordinate system. So what I'm doing is, if I have a fluid flow like this, I'll be considering a cubical portion. Okay, a particular cubical portion is considered. Okay, and that cubical portion I'm going to consider. So suppose this is that cube. Okay, this is that cubical portion of a fluid flow. If that is the case, this is plane 1, plane 2, and suppose this is, okay, I'll use another color. This is X direction, this is Y direction, and this is Z direction. If so and so, plane 1, the fluid is entering, and through plane 2 the fluid is flowing out. Okay, so the forces this cubical body may experience, so we'll be analyzing force in all those three directions, X, Y and Z. What may be the forces we have to consider? Gravity force is there, and in fluid viscous force is there, being fluid. Then pressure, obviously pressure force is also there. So how can we analyze this? We'll just see. Suppose if pressure at, if I'm considering X direction, Px, or suppose if Px is, and gradient along X direction for pressure, if that is dou P by dou X, and if this if we have considered a cube and the dimensions, let the dimensions be delta X, delta Y and delta Z. Then the change that the pressure may undergo after the fluid reaches the second phase of the cube we have considered is dou P by dou X into delta X. So at plane 2, what we can say, it is nothing but P plus dou P by dou X into delta X. So that is about pressure. If viscosity is the thing we have, or the viscous force, it is represented by tau. Similar thing only we will be getting, tau plus dou tau by dou X into delta X. If gravity force is considered, suppose gravity force be represented by simply the simply Fg or something. Okay, obviously we know along X direction and Y direction there is no change in gravity force. See, the gravity force only acts along z direction. So x and y direction, even I'm saying let that be fg, then what it be? What that at plane 2, dou fg by dou x into delta x. Similarly in y direction and z direction. So we have considered a cubical portion. We have to consider a cubical portion in a fluid flow to start analyzing on it. So what we are going to do, we are applying Newton's law, that is any acceleration produced is due to a force. So when we are considering that fluid element, two forces may act, that is the two forces are expected to act on any element, that is one is body forces and surface forces. Body forces and surface forces. Body force is nothing but the due to that weight or mass, simply the force due to gravity, and that is we have to get density times volume times it will be mass times g. So it actually acts in one direction only, that is if we are considering a coordinate system x, y, z, and is said to be perpendicular to Earth's plane of Earth, then that is the direction we are considering that gravity force is acting along is the direction. So how you set the coordinate system, that depends. Now surface forces. See, surface forces are shown here, that is normal stresses and the shear stresses on the fluid element, sigma yy. Now if you are considering x direction, sigma x is there acting perpendicular to the plane y is z. So the force in that direction can be sigma x times, suppose the dimensions of the cubical element we have considered is delta x, delta y and delta z, then force due to sigma x is sigma x times delta y, delta z. Okay. Now tau x is and now in x direction what all forces you can find further? Sigma x is there, then tau zx. Tau zx is acting in a plane delta, acting in a yz plane. So tau zx times xy plane, delta x times, that is tau xz, if we are considering it acts in a plane delta x, delta y. So what is that force? Tau xz times delta x, delta y. Okay. Similarly, in x direction, tau yx is there. It acts in a plane delta x times delta z. I think you are getting what I am up to. So, one more step you have to think about. Here I have just described that. Now, if along the cubical element, from one surface to another surface, suppose that if we are considering yz plane, we have two such planes here, this one and this one. See, so from one plane to another plane, the magnitude of these stresses change. Okay, so forces also change. Similarly, here we have one force F acting in the first plane and F acting in the second yz plane. Okay, when we are applying Newton's law, we have to take the difference of these two forces equal to mass times acceleration. That is what we are going to do. See, here we have in first plane the stress acting is taken as sigma xs minus dou sigma xs by dou x. The variation along this cubical element we have considered as dou sigma xs by dou x times delta x, where delta x is the dimension of the cubical element. Times, to convert it into force, they have multiplied the whole thing by delta y delta z. Now in the second plane it is sigma xs times delta y times delta z. So the difference of this force we have to consider in x direction. But the other things we have to consider, tau zx is acting in x direction, tau yx. So we have already said that. Now tau yx varies in y direction. See. So when we are taking the sum of these two forces, that is tau yx minus dou tau yx by dou y delta y times delta x delta z plus tau y times delta x delta z, net will be dou y delta y times delta x delta z. I think you are getting my point.
So what we have done? We have taken a cubical portion of the fluid flow. The stresses acting on that fluid element can be described as shown in the figure. We have shear stresses along the plane. See, if we are considering x direction, tau xy and tau xz, and normal stress sigma xx. So, suppose we are analyzing the fluid element along x direction using Newton's second law. We will be getting rho times mass is rho times delta x, delta y, delta z, provided these are the dimensions of the cubical element we have considered, times acceleration along x direction is equal to respective forces. See, I'll show one more diagram. Sorry. This figure shows the changes in stresses along the direction. See, if we are considering x direction, sigma xx has changed from sigma xx minus dou sigma xx by dou x times delta x to sigma xx. That is, this is the variation that has. Similarly for other things, tau xy by dou x into delta x is the variation of shear stress. This is the shear stress tau xy. It has undergone a change of this much. So what will be the force acting on that fluid element? Change in stress times the area, cross-sectional area. So and so are the stresses. So this is, so this can be equated to what? That change in stress times cross-sectional area. Sorry, I haven't multiplied the area. tau xz. So these three. Sorry, one more thing. In x direction only we have to consider. This tau xy and xz are acting in some other directions. Along x direction, what we can see? I'm sorry for that. Along x direction we have tau yx, tau zx, that on some other planes only. That is, along this plane we have in x direction tau, perpendicular to this plane we have y, tau yx. So though tau yx delta x, it acts on a cross-sectional area. Now, how it varies, there is another thing too. By delta x into delta x, it acts on a cross-sectional area. Delta x, delta z, and it varies along tau, it varies along y direction. Delta. Another thing we have is zx. By dou tau z by dou z times delta x delta y time. The cross-sectional area is delta x delta y. Hope you are getting what I am going to. Now, one more thing you have to learn about. This acceleration can be given by variation of velocity. So dou x times dou x with respect to time only. By dou y times dou t plus dou u by along z time dou z by dou t plus dou u by dou t. This is how we give acceleration along its direction. So u dou u by dou x plus v dou u by dou y plus w dou u by dou z plus dou. Since why this happens, so and so. X is a function of u is a function of x, y, z and t, and we are taking variation of dou u by dou t. So variation of a function with a number of variables is given like this. Now similarly, if we are considering dou, suppose the considering dou yx, it is given by mu plus mu dou v by dou x. So variation of dou yx along x can be given by mu dou square u by dou x dou y plus mu dou square v by dou x. Similarly, if we are considering zx, nothing but mu dou square u by dou x. Zx, dou zx is given by mu dou w by dou x plus mu dou u by dou y z. So again integrating with respect to x, dou square and dou square u by dou z. I think you are getting into my point. See, we have see we have z here, so w term prime and x only, x here, so u and with respect to z. Perpendicular direction only will be, so because we are taking velocity gradient, that is, if the fluid flow is like this, if this is the velocity v u, that is in its direction, we are analyzing its variation along y direction. That is why we have taken just opposite direction or perpendicular direction. Just this normal force sigma h is given by now we can just substitute everything there. What we have got ax, we have got as u dou u by dou. Instead of writing everything, we can write simply as dou u by dou t plus what is this term? Sorry, this visually. Dou u by dou x, dou u by dou y, dou is plus that are gradient, and it is del u and v dot del v. This is dot product. And rho mass times this acceleration, rho del x del y del z times this acceleration is that equation only we are substituting this. So that is this one. Here one more thing, we can have this del h del y del z cancelled everywhere. Remaining we have rho ax equal to sigma x square and dou that is we have the equation as rho ax and I think you are clear about this direction of shear stresses along tau yx, how we got tau yx by dou y because its variation happens along y direction. Similarly, tau zx, its variation happens along z direction. So by dou z only. And we have derived the equation for them also, that is mu dou square u by dou x dou y plus mu dou square v by dou x square plus mu dou square w by dou x square plus mu dou square u by dou z dou x. So this can be given by with, so I'm substituting that in here. U dou square u by dou x dou z plus mu dou square w by dou x square. So just taking dou u. So I'm substituting that in here. U dou square u by dou x dou z plus mu dou square w by dou x square. So just taking dou u.
Now mu dou square u by dou x dou y plus mu dou square u by dou x dou z, we can write that as, we are taking mu dou u by dou x common, dou u dou by dou x, if we are taking dou by dou x common, we will be getting dou u by dou y plus we have used the capital only, plus dou u by dou z. So we will be getting it as mu dou square u by dou square. So finally the equation will be, we will be getting the equation as rho dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z is equal to, now we have that term sigma, dou sigma x6 by dou x. Now sigma, that stress term is the normal stress. So for any plane, normal stress we can consider it to be pressure. Pressure means it is causing compressive. In normal stress we are considering outwards or away from the plane as positive, since pressure is a compressive force, so we have to use negative sign here. So I can write it as minus dou p by dou x and plus what all terms we have coined up, mu dou square u by dou x square plus mu dou square v by dou x square plus mu dou square w by dou x square. In this way we can write in all directions. That is in and one more thing we have, that body force also. In all directions, that is similarly in y direction you have rho dou v by dou t plus u dou v by dou x plus v dou v by dou y plus w dou v by dou z is equal to minus dou p by dou x plus mu dou square u by dou y square plus dou square v by dou y square dou square. And so what all things we have changed here, you have changed, then these things. Similarly, in Z case, if we are considering Z term. While we are considering Z term, one more change will be there. Here you have to change everything to W, and Y will be changing to Z. And one more change you have to note, that is in Z direction, this normal stress that is perpendicular to Z plane, that plane or xy plane, it has normal stress other than pressure force. We have to consider gravity too. So plus rho g is also there. Rho g is also there, which is, that is how it came. I will say that gravity force is rho, density times volume is delta x, delta y, delta z, times g is the force. Now while we have constructed the equation, we have divided all terms by, if you are remembering that, delta x, delta y. In first equation, we have divided all terms by delta y, delta z. In while constructing that equation in y direction, we have to, from the basic, if you are referring backwards, you will get that point. So it is nothing but rho g delta z. Now these equations are called Navier-Stokes equation. Finally, we will be getting the equations this way now, which we have already told. This is in x direction, y direction is a direction. Now these two terms we don't have to consider, because I have already said body force acts only in Z direction. So in final equation only we just have to note it, considering gravity force is acting in Z direction. So that is it. Now these equations are called Navier-Stokes equation. These are the so-called Navier-Stokes equation. Now from this only we are going to derive Eulers equation. For that nothing we have. In Eulers equation, they neglect
So we will consider Euler's equation is a direction. That is and in Bernoulies equation, we consider the flow to be steady. That means steady and incompressible. one term rho is there, and steady means with respect to time it can be considered to be 0, and
So in Bernoulies equation, one more condition is there, that is the flow is irrotational. For irrotational flow, the condition is del cross V equal to 0. Velocity component equal to 0. Now we have our Eulers equation as dou V by dou T plus V dot del V dot del V equal to minus del P plus rho G. Where we will be substituting now this del cross V equal to 0. There I am going to define a new term, velocity potential. That is V equal to del phi. So this will be satisfied. So that this will be satisfied. Now this V can be substituted as del phi. Dou phi by, so that will be giving you dou phi by dou T plus del square phi. So this is our Eulers equation, and for Bernoulies equation we have one more assumption, that is the flow is irrotational. Irrotational means del cross V equal to 0. So from this we are defining a new term called velocity potential, where V is del phi. So that del cross V is equal to 0. Now I'm going to substitute this del phi here, and when we are taking this del common, and we have dou phi by dou T plus, now del phi, this will come to be del phi dot del of del phi. So if this del is taken as common, we have that as del phi whole square, and this is equal to minus of So I'm taking all this to this side. That will be plus del P. So plus P equal to rho G. And we are considering which direction is a direction. So that this rho G is, when rho G is taken into consideration, it is clear that it is a direction. And if or minus rho G equal to 0, and if then I am integrating this, what we will be getting? Del will be removed. Dou phi by dou t plus del phi whole square can be written as v square by 2 plus p minus rho G z is some constant. So this and now applying the other condition that it is steady, it is applicable for steady, this dou phi by dou t can be neglected. Since Bernoulies equation we are applying it only for steady flow, variation of variable with respect to time can be considered to be 0. So the other things, if we are writing P by rho G plus half 1 v square by 2 minus z equal to constant is sorry, there have been a mistake that is in the previous slide. There is a mistake in the last steps, that is it is rho, I have not considered rho del v, rho dou v by dou t plus rho into v dot del v equal to so and so. So we have rho there. Finally Bernoulies equation we will be obtaining as P by rho G plus v square by 2G, and we have minus z, and for that if we are taking from higher level to lower level, that is h2 minus h1, that is the way we are taking. While integrating, it can be taken as plus z, that is while integrating it is h2 and h1 delta z. Okay, this is the term. It will be turning to h2 minus h1 negative of. So from datum, datum is what? h1. We are measuring how much high it is. So positive means from bottom to top we are taking. So it can be written as plus z equal to a constant, which is our Bernoulies equation. That is P by rho G plus v square by 2G plus delta z, or z, how much high it is from datum, is a constant. So what is this indicates? P by rho G, there is a term, then v square by 2G with another term, and z. So this is velocity head, the energy the head or the energy possessed by the fluid due to its velocity. Now P by rho g and Z, it is piezo, they both are together called piezometric head. P by rho g is pressure energy, Z is datum head. The energy possessed by the fluid due to Z is nothing but due to its height difference. So simply Bernoulies equation tells us can also be derived from the thing that kinetic energy plus potential energy is the total energy. This total energy is always a constant. From that only we are getting the same. So